Oh, I need to press record on here as well. Right. Here we go. So this is this week's homework. The curve y equals ln x is transformed by an inflection in the x-axis, followed by a stretch of scale factor 3 parallel to the y-axis, followed by a translation in the positive y direction by ln 4. Find the equation of the resulting curve, give your answer in the form y equals the natural log of some function of x. Well, it's not as bad as it looks at first. We've got 3 transformations, but they're kind of all in the same sense, aren't they? They're all parallel to the y-axis things. So our reflection in the x-axis, that means that our function is going to become negative. Whoops. So we're going to have minus the stretch of scale factor 3 parallel to the y-axis. Well, that's the 3 times the whole function, isn't it? If we do it in function notation, this is a minus 3 f of x, and then followed by a translation in the positive y direction by natural log of 4, so plus and then 4. So that's what the function looks like in terms of function notation. We have to write it as the natural log of a function. So this is minus 3 times the original function is ln x plus ln 4. So we've got a little bit of tidying up to do with that. Before we can combine these, we need to have them both as 1 times natural log of something, before we can have them together. So let's write this one as being the natural log of x to the minus 3 plus the natural log of 4, because that's our third law of logarithms from our Core 2 poster. And then if we add these together, we're going to have the natural log of 4 times x to the minus 3, or if you want, the natural log of 4 over x cubed. And either of those would be a suitable correct answer for the 4 marks, and it looks like quite a nice 4 marks like that, doesn't it? So that's mark that. There we go. Good start. Okay. The next one is was the big question. Huge number of marks for this. The function f is defined for all real values by of x by f of x is e to the 2x minus 3 e to the minus 2x. Show that the gradient function f dashed x is bigger than 0 for all x. So the first thing we're going to have to do is to differentiate this. I'll go down here to do it. So what was the function? F of x was e to the 2x. Was it minus 3? E to the minus 2x, have I remembered that right? Yeah. So if we differentiate that, differentiate e to the ax, and we get ae to the ax. So that's going to be f dashed x would be 2 e to 2x. And then if we bring the minus 2 down here, that would make this a plus 6. E to the minus 2x. Remember, when we're differentiating e to the something doesn't change. The power doesn't change, we differentiate it. So that's f dashed x. The question said, show it's bigger than 0. Now, we are actually going to have to show that it's bigger than 0. And so we need to make some statement. We can't just say that it's bigger than 0, there you go. So we need to come up with some kind of coherent statement about this. Now, one thing that we do know is e to the x is greater than 0 for all real x. Okay. Therefore, e to the 2x must be greater than 0 for all real x. And if that's true, we're adding 2 positive things together. So 2e to the 2x plus 6 over e to the 2x. They must both be positive as well. Must be greater than 0 for all real x. Hence, it was f, wasn't it? F dashed x is bigger than 0. Okay. It's not a big deal, but we do actually have to write something that explains why what we've got is bigger than 0. Part B. show that the set of values for which f double dashed x, the second derivative, is bigger than 0 is the same as the set of values for which f of x is greater than 0, and state what this set of values is. I guess there's two approaches here. You could either go for the approach which kind of does it the other way round and says that let's find the set of values for which that one's positive and find the set for which that one's positive and show it's the same thing. But there's a neater way of doing this. We need to differentiate again to start with, don't we? So this is part 2, isn't it? F double dashed x would be 4 e to the 2x. If we differentiate 2e to the 2x, we get 4e to the 2x. And then that's going to be minus 12 e to the minus 2x. And we look at that and we think there is a common factor of 4 in this expression. Once we've taken out our common factor of 4, then we realise that actually we've just written 4 times the original function, haven't we? So the second derivative is the same as 4 times the original function. Therefore, what we can say from that is that if the set of values would be the same, wouldn't it? If f of x is greater than 0, then 4 times f of x is greater than 0, and that is greater than 0 for the same set of values. So now we need to find what that set of values is, and we can work with either of the bits of functions that we're dealing with. If we've just shown that it's the same set of values, then let's work with the simpler bit. So we now want to say when is, if f of x is bigger than 0, that means that e to the 2x minus 3e to the minus 2x is bigger than 0. We want to try and solve this inequality. You could do this first stage however you want to, but I'm going to think, if I do anything else, that means that, doesn't it? E to the 2x minus 3 over e to the 2x. So let's multiply through by e to the 2x. Now remember, we've always got that thing to watch out for, that if you've got an inequality and you times both sides by a negative number, you have to change the sign around. But we've already established quite a few times that e to the 2x must be positive, so we've not got an issue here. Multiply that by e to the 2x and we get, e to the 4x, because you would add the powers, minus 3 is bigger than 0, so we're saying e to the 4x is bigger than 3. Take natural logs of both sides, 4x is bigger than natural log of 3, and so x is greater than 1/4 of the natural log of 3. And I'd probably like that left like that. You could write natural log of 3 to the quarter. It didn't specify a particular form. So that's it. So that's the 5 marks for that one. And still the question goes on. We've now got the function g is defined for all real values of x by that, which is similar, isn't it? All that's happened is that instead of the minus 3 we had up there, we've now got a plus k, where k is a constant greater than 1. The graph of y equals g of x is shown above. Find the range of it. Well, if that's the graph, then that would suggest that we have a turning point, and if we can find the turning point, the y-coordinate of the turning point, that gives us our range, doesn't it? So what we're interested in doing here is to start with, we need to find the derivative of g of x, and then we can find where the statement point is. So we're on part 2, I'm sorry I labelled that wrong before. But we're on part 2 now, and we've got g of x is e to the 2x plus k, e to the minus 2x. Let's differentiate it. 2e to the 2x. This would be minus 2k, e to the minus 2x. And we would like to know when is this equal to 0, because that's where our stationary point is. At the stationary point, g dash x equals 0. So 2e to the 2x minus 2k e to the minus 2x is equal to 0. I've run out of space on this page. Hang on. What am I doing? Look at that. Effortless. There we go. So we're there on a new page now. And I don't know why I did that. Then we've got e to the 2x and we've got e to the minus 2x. So let's do that same trick again of multiplying through by e to the 2x to get 2e to the 4x minus 2k is equal to 0. If we rearrange this, we've got e to the 4x equals k. I've divided by 2 at the same time. So taking natural log of both sides, 4x is equal to that. It's quite nice to be able to write that, but make sure you don't do it in pencil, because it's got to be ink. So x is 1/4 ln k. Come on, I'm trying my best. That was a good joke. Right, that's the point at which we have the stationary point, so that's not our answer in itself. We need to know the y value, that's what we said. So we now need to know what value that would give us. So sub it back in. So g of 1/4 ln k would be e to the twice that, e to the half ln k plus k e to the minus a half ln k. And so that is our lowest value on the graph. So the range is g of x is going to be greater than that. It did say give your answer in simplified form. So we need to do some work with this because that's a bit of a mess, isn't it? Now let's think. If we could get this half, so it wasn't there in front of the ln, then we could just undo all of that. So this is e to the ln root k, because it's k to the half inside there. This is plus k e to the ln, and that's k to the minus a half, isn't it? So that's 1 over root k. So we've got e to the natural log of root k, which is root k, plus k times 1 over root k. And, well, that's great, which is root k plus k over root k would be root k. Okay? Okay. So that's 2 root k. That was a good one. Right, so that is our minimum value. What we just established is that is the, it's on the other page. That's the y value. Chaos. It's the y value of that point there. So the range, finally we have an answer. The range is g of x greater than or equal to 2 root k. Go.
I got to the bit where it was the unsimplified form, so that's
Yes.
the top bit. But then I went wrong in my simplification, so how many marks did I lose?
How many marks? It was 5 marks altogether, was it?
Yeah.
What do we think? I think you're probably going to get 4, aren't you? Because we had a lot to do here. We had to differentiate it, and we had to put that equal to 0. So that's probably 3 marks just for doing that. A 4th mark for getting to the unsimplified value, and then the final mark for turning it into a simplified range. Did you say you never got to the point where you said g of x was greater than that, did you?
I said the range of g of x is greater than my value.
Definitely 4 then. Yeah. Okay.
You know when you get k over root k,
Yeah.
how does that equal root k?
Because that's k to the 1 divided by k to the half.
8 more arcs.
And you subtract the powers. Does that make sense? So 1 minus a half, which is a half. I think we're done. And that's maths.